So first of all, thank you, Python Ireland, for giving me this opportunity to present the talk titled Quantum Computation with Python. Myself, Harshdeep Singh. I'm currently doing PhD from CCDS IIT Kharagpur. And the agenda of this talk would be to give an introductory talk about quantum computation. If you are from science or technology background, you might have seen your favorite computational techniques or any other tech stuff getting quantified. So a quantum is being added in front of it. So before delving into too much into what the like advances are, so let's take a step back and see from the beginning, the starting, the basic concepts of quantum computation, what quantum computation is, the physics and maths required, and how to build basic quantum circuits using Python's Qiskit, IBM's Qiskit library in Python. So first of all, what is quantum computation? It may be divided. I sure. Yeah. So it may be defined as developing algorithms and computational techniques based on quantum mechanical principles. As a lot of you might be aware of that, most of our computational techniques are based on classical mechanics. And now we are trying to move towards the quantum mechanical principles just because of the availability of qubits right now. And so we are trying to develop at least the algorithms, the theory behind quantum computation. If you ask why is it needed, if we have a working theory of classical computation, why do we need quantum computation anyways? So Richard Feynman very famously said that if we want to simulate nature, if we actually want a proper simulation of nature, of what atoms or what these quantum mechanical objects look like, we have to make them quantum mechanical, because that's what reality is at that level. So with that in mind, we move towards quantum computation. And also theoretically, the quantum computing promises a very significant advantage over all the classical machines. So if in case you have heard, Google's quantum computer did a simulation of a quantum circuit that it had to sample over 1 million times. It did that in 200 seconds. And the fastest supercomputer that we have available today, working on the classical computation methods, would take around 10,000 years to do the same simulation. So you can at least get the scale of what we are getting at. So that is why quantum computing becomes such an important part, and why it is such a like rage these days. Like everybody wants like to get something out of quantum computing, because it is very promising. So before going into properly into what the components of quantum computing is, I'll like to introduce what is a bit, because I think the language is important. For any computation, the language is important. And bit, as you might know, there's ones and zeros. It's the most generalized unit of information. So the term bit itself is formed by contracting binary and digit. So any state with two possible configurations, true or false, 0 or 1, whatever it is. So you might have seen in any computer languages, usually the inputs and outputs, so the outputs actually, the inputs are given in form of these zeros and ones, strings in zeros and ones. So we use these bits to represent numbers, alphabets, and by extension our commands. But why are these bits so important? So see, the point is that the computers can't understand our language, but what they can understand is whether a switch is on and off, whether some current is flowing, whether a statement is true or false. So these logical statements are inherently there for our computer machines, or our classical machines. So that is why these bits become so important in logical expressions and in machine learning or in computer languages. Once we have the idea of bit, now we can introduce the quantum version of bit. So what the quantum version of bit is, so essentially, if bit is the fundamental unit of classical information, qubit is then a fundamental unit of quantum information. And like the bit, qubit also has two states, either a 0 or a 1. And it is written in a slightly fancy way. You will see these a lot during the next, I think, half an hour. So these like notations, these are essentially quantum notations, but 0 and 1. So this is how we represent bits. And just like classical systems, both of them are orthogonal. So orthogonality means that if you are in one of the states, then you are definitely not in the other state. So for example, if you have a coin and it lands on heads, then you can with certainty say it's not tails. Very trivial thing, but to keep in mind. So their states are orthogonal. This is what orthogonality means in general. And the one major difference between bits and qubits is that qubits can exist in superposition of the two states that are available here, 0 and 1. Now, what this superposition technically is, I'll just explain it in the next slide. So quantum superposition principle. So generally speaking, the quantum superposition principle is defined as the property of quantum system to exist in multiple states at the same time. So what actually I'm talking about here is that not only we have these two states, but we also have all the linear combinations that we get out of these states. So all the linear combinations, in the sense, in any way that you can add these states is also a possible state, subject to one condition, that alpha square and beta square should be equal to 1. This concept is known as normalization, and alpha square and beta square represents the probability of being in these states. So anybody not from physics or science background might find it a little bit difficult, because superposition principle is such a uh, concept which is embedded in even classical electrodynamics, statistical mechanics, and in quantum mechanics, that we get used to it. So just for being in a safe side, I'm trying to explain it in the most like layman term as I could. So let us say uh, every quantum state is written, which is written in this form, is actually a coin spinning in the air. So what you can say is that this shy state, this is known as shy, by the way. So this is a spinning coin in the air, and what you can do is you can catch it and have a look at it, and this process is known as measurement. So when obviously if it's a coin spinning, if you catch it and look at it, it's either gonna be heads or tails. So it's either gonna be 0 or 1. But how many times, if you catch it multiple if you do multiple measurements, how many times you will get 0 or 1 is decided by these alpha and beta. That is why they were known as the probabilities. So I'll explain it with a simple example. So let us say we have this state. In this state, alpha is 1 by root 2 and beta is 1 by root 2. So alpha square and beta square both become 0.5. So let us say if you have 1000 states like this, and we perform these measurements. So you have 1000 of these coins, and you're catching all of them and looking at it, what you get, either a heads or a tails, either a 0 or a 1. If alpha square and beta square are 0.5, then we expect 500 of them to give us 0 and 500 of them to give us 1. So this is what the superposition means. So essentially this is somewhere in between, like these are states which are not definite but depends upon the measurement. So sometimes it might give you a 0, sometimes it might give you a 1, and it depends upon these alphas and betas, that how many times you will get a 0 and how many times you will get a 1. Another very simple example would be this one. So 0.8 into 0 and 0.6 into 1. So in this case, you have the alpha, which is alpha square, which is 0.64, and beta square, which is 0.36. So now if you do the 1000 tosses again, so 640 of them, because 0.64 is the probability of 0 state, 640 of them would be 0 and 360 of them would be 1. So this is in a nutshell what quantum superposition principle is. So I hope you get the basic gist of it if you're not from the, again, technical background. So the easiest way that I could represent qubits in mathematical form or in some sort of physical integration form is the matrix formulation. So what we know so far about qubits is that they are two-dimensional and they are orthogonal. With this in mind, we can represent the qubits in this form, in these matrix notations, 2D matrix notations, so 0 and 1. So you can check, obviously these are orthogonal if you do the like a simple dot product of these. So once we have that, everything becomes kind of easy, because you can see, let us say you have this general state which was written as alpha 0 plus beta 1. Now alpha is obviously 0. Now we have seen it's in 1 and 0 form, and 1 is in 0 and 1 form. So now your Chi becomes a simple two-dimensional matrix, two-dimensional array with alpha and beta. So the first component will give you the probability of being in the 0 state, and the second, this beta will give you the probability of being in the 1 state. So see, as we introduce the matrix notation, everything becomes a little compact. So the symbols go away, these brackets go away. So it's quite simple to see, and even the matrix operations becomes quite easy. The other, I'll just like to point out, the other representation is the block sphere representation. So in which you essentially use a sphere to represent the qubit. I personally don't like that like representation, because it becomes very difficult as the number of qubits start increasing. So if you have 2-3 qubits, then you have to like take into account all these different spheres. So in that cases, matrices becomes the only way. So that is why I've kept matrices as the starting point. I hope it is somewhat clear to you right now. So next is multiple qubits. So let us say you have more than one qubits. In that case, you have to use something known as a tensor product. So obviously there is a lot more mathematics behind, but I'll just use the matrix formulation to tell you how we write these tensor products, how we do these tensor products to write these multiple qubit states. So the basic, this bracket notation is very quite easy, because if you have two qubits, you just write in terms of this. So one qubit and two qubit and this product sign in between them. And we can even simplify them by using a direct notation 0 0. So the first qubit is 0 and the second qubit is 0. And obviously if you have two qubits, you have four possibilities. So 0 0 0 1 1 0 and 1 1. So in this way, you can represent then three. In the case of three qubits, it will be 0 0 0 0 1 and so on. So 2 raised to power n. So n is the number of qubits you have. That many states you will have. The matrix notation becomes very easy in the sense. So let us say you had these two qubits. So what this tensor product means is that you take the first element of your first qubit and multiply it with both of the elements of the next qubit. So 1 into 1, the first element becomes 1 of the two qubit system. 1 into 0, this becomes 0, and 0 0 into 1 0, and 0 into 0 0. So in this way, it's very easier to construct multiple qubit systems with the help of matrix notations. So quite simple, you take the first element, multiply it with both elements to get the two elements, and then the second element of the first qubit multiplied with the both elements of the second qubit, and you get the if you have two qubits, you get a four component matrix. Once you have that, you can replicate that for each of the four cases that I talked about. So 0 0 0 1 1 0 and 1 1. In this way, you can obviously form the three qubit, four qubit, and so on. As of this lecture, we won't go further than the two qubit system. So that is why I haven't been discussing that. With that, the last thing that I need before I can completely move on to Python is the quantum operations. So quantum operations are nothing. So quantum operations, anything that you can use to manipulate or change your states, is known as a quantum operation. And they are generally written in terms of matrices. So for example, if you have a single qubit, a 2 cross 2 matrix multiplied by a two-dimensional array would give you a new two-dimensional array. So this is somewhat what a quantum operation is in matrix notation. So let us say in this case, this Z operator is 1 0 0 minus 1. So its job is, if you multiply the 0 qubit with it, you will get a plus 1. And if you multiply the 1 qubit with it, it will give you a minus 1. So this is more or less what operations mean. So you apply an operator, you apply a matrix, you get a result, or you get a new state, one or the two. Once we have that, now with this information, we redefine what quantum computation is. It's similar to logical or digital computation or digital processing, but instead of bits, you add qubits. Instead of logic gates, you add quantum gates. So that's pretty much it. Quantum gates are usually called the operators, and operators, as they suggest, you do measurements, manipulations, all this stuff. And one of the most commonly known operators, if you know, is the Hamiltonian. So if you apply that on a physical system or a chemical system, you get the energy back. So things like that, position operator, momentum operator. So these are the basic operators that you can get. So now we can actually move on to the Python part. I have taken very long to introduce, but it's a very hectic, like theoretical part is quite large, and I still think I have moved very quickly. But yeah, the first quantum circuit. So what we are going to do is, now the first thing is obviously we install Qiskit in our machine, and we import the required libraries. So the required libraries in this case are quantum register, classical register, and a quantum circuit, and a visualization tool. Any tool that will help you visualize what are the results that you're getting. We'll get into it in a bit. So first part is how to create qubits, how to create these qubits using Qiskit. So this command known as quantum register, and then the number that you provide. The quantum register, what it does, it gets you these qubits, and the number is the number of qubits that you get. So in this case, this qubit variable stores one qubit. And now what happens is that since qubits can exist in superpositions, you need something to store the result of your calculations. So let us say that spinning coin example. You catch a coin, it turns out to be heads. Now you want to store it somewhere. That storing purposes is taken care by these classical registers. So rule of thumb, the number of qubits you have, try to have that many number of classical registers, so that whenever you do a measurement, you store it somewhere. So how we do that? By quantum register, the number of qubits that you want, classical registers, the number of classical registers you want. So now in qubit, you have your qubit variable, you have your qubit classical, you have your classical registers. So now you make your first quantum circuit by calling these variables into this command quantum circuit. So you have prepared a quantum circuit with a single qubit and a single classical register, and this is how the basic like canvas looks like. So this is how a quantum circuit would look like without any operation, without any measurement, without any. So this is what a default circuit looks like. So what we can do is we can try to do the measurement, so that catching of the coin, and then trying to see what we are getting. So this is the command that we are looking for right now. Circuit. So this is our circuit dot measure 00. 00 means the measure the result of the 0th qubit and store it in the 0th classical register. So obviously in Python, indexing starts from 0. That is why. So 0 to 0. So by the way, this MPL is a drawing technique. If you don't do that, it will draw it, but in a very like elementary way, so it won't look that nice. So that is why it's you can try without that as well. It won't make a lot of difference, but it just looks nice. This circuit display circuit dot draw in the quotes MPL, it's a drawing tool. It helps us to do better visualization. So now you have a qubit, a default qubit, you are adding a measurement and you're seeing what you're getting. So whatever you are getting right now is what default qubits value will be. So if you just call a qubit by default from Qiskit, the value would be 0, by the way. So now I'll just spend a few seconds talking about simulators. So what happens is that, so you can obviously work in actual quantum computers. So IBM is known for providing this opportunity to us by IBM Quantum Experience. So you can actually send your circuits to actual quantum computers, and they can compute and send back to you the results. But obviously that process is little time consuming even for the very small circuits, and this is so literally no circuit at all. So what you can do is there are things called simulators. So these simulators simulate what a quantum computer would do on your classical machines. So in this case, the simulator that we are using is Qiskit AIR's QASM simulator. So we store that in this simulator and then we execute this circuit. So we had this circuit and now we are executing this with this simulator, and shots is how many times you are doing it. So for example, that toss example that I will be using again a lot in upcoming slides as well. So how many times do you want to do this measurement? So in this case, we do this circuit execution 1000 times, and we see, since we haven't added any like operations, so we are getting a 0 1000 times. So result is, so this job is the execution of the circuit. So from this job parameter, we get the results, and this result has a lot of other parameters, the state vector, all these things that probably won't be needed within the context of this lecture. So what we can do is we can get counts from that. So get counts is essentially a parameter which stores how many times you got which state. So in this case, we have got 0 1000 times. I hope this is somewhat clear. So next is, up until this point, we haven't added anything in this circuit. Our circuit was just a qubit and just a classical register, and we were doing a measurement, storing it, and we were seeing what the default value is. So default value is 0. Now what we can do is we can do operations. We can add gates, we can add operators into our circuit, do the manipulations, and all the good stuff, as I say. So the simplest one is not, I guess, because this is very much there is in digital like circuits as well, classical circuit as well. So what NOT does, it takes a 0, turns it into a 1. It takes a 1, it turns it into a 0. So that is what NOT does. So this is how we represent it in like this bracket notation. So x0 turns it into 1, x1 turns it into 0. In matrix notation, it becomes much more simpler to see. So let us say we define a x matrix like that. So x0 becomes x into 1 0. So it turns it into 0 1. So simple matrix multiplication, and 1 x acting on 1 0 1, it turns it into 1 0. So this is how it works. So this is what I meant. The matrix multiplication makes it, matrix representation makes it much more easier to understand what is going on, because then you can actually see the mathematics behind it rather than just assuming that okay, this is happening. So next we will try to execute this. So we had a circuit in which there was a single qubit and a single classical registers. So now what we are doing is we are adding a X gate at the 0th qubit. So this is what this command means, an X gate at the 0th qubit. And then afterwards we are doing the measurement. So measurement again from 0th qubit to the 0th classical register, and then we are drawing the circuit. And this is what our circuit looks like. 0th qubit, it's flipped and then measured. So just before going to the final result, this is what we expect. So the qubit by default was in the 0 state. Now we have flipped it. So what we expect is all the times, all 1000 times, 100% of the times, we should be getting 1, because 1000 times it was in the state 0 and it has been flipped to 1. Again, the whole process, we have to call the simulator, we have to execute the job, and we have to get the counts. And as you can see, we are getting 1000 times of the time, or 100% of the times. In probabilities, it's normalized. So this is how we add operations. This is how we create basic circuits. So I'll try to like pace it up a little bit, because I have a little bit more to cover. Otherwise, yeah. So there are different types of operations that you can have on qubits, broadly classified into two parts: one qubit operators and multiple qubit operators. And as the name suggests, one qubit involves only a single qubit, and multiple qubits involve multiple qubits. And there are a few properties which are common in all these common quantum operators. Again, this is a bit more mathematical, so I'm not going to delve into a lot of them, but they are Hermitian, they are unitary, and they are reversible. What Hermitian means is that whenever you apply an operator or something, whatever the answer that you get, whatever the measurement that you get is real. That is, I think, more or less the takeaway from this. Other than that, yeah, unitary and reversible, it's not going to be needed for the scope of this the next presentations. So one qubit operators, two of them we have already seen. So Z we saw in the first example, and X we saw. So the flip one, the not one we saw, but the most important by far is the Hadamard operator. So what the Hadamard operator does, it takes a single state and turns it into a superposition. Now think about it. The main difference between qubits and bits is that qubits can exist in superposition, and this operator does that job for us. So this operator, that is why it becomes so important. So what it does is, so let us, so this is the matrix representation of this Hadamard operator. So 1 by root 2, 1, 1, 1 minus 1. So when it is applied on the 0th qubit, it gives us 1 by root 2, 1 and 1. So we can write it as 1 by root 2, 0 plus 1. So what it does, it takes a 0th a qubit in 0 state and turns it into a superposition of 0 and 1. Similarly, it takes 1 and turns it into a superposition of 0 and 1. This minus sign, just to be clear once more, that the beta, the probability is actually mod of beta square. So this minus sign doesn't play a lot of role in it. It adds a phase between the two states, but for all the practical purposes, they are generally they don't play a lot of role unless and until you are doing some other calculations. For our basic calculations, the sign won't play a big role, because it's again mod of beta square. So what we can do is, in simpler notation, this is how we can write that, just for memorization purposes. It will be needed later on. So if h is applied on 0, we will get 1 by root 2, 0 plus 1. And if it is applied on 1, 0 minus 1. So we can execute the same thing in Python, in Qiskit. So now this is an easier way. So I was talking about there is a much easier way to construct a quantum circuit. So we don't have to choose different variables for classical register and then a quantum register and then add it. So we can directly say quantum circuit 1, 1. What does mean is, there is a quantum circuit that we have created with 1 qubit and 1 classical register. There is a single qubit, there is a single classical register. Then what we are doing is, on the 0th qubit, we are adding a Hadamard gate. So dot H0 is the Hadamard gate. And then we are doing the measurement like we have done previously, from 0th qubit to 0th classical register. And then we are drawing the circuit, and this is how the circuit looks like. So 0th qubit, Hadamard gate, and then a measurement. So what happens next is that it was in the 0th state. Now we are seeing a 50-50% probability, what we were going to expect like from the math that we saw. So right now we started in the 0th state. Now we are in a 50-50 probability between 0 and 1. So this is what Hadamard gate does. So next is another very important part, which is the multiple qubit operator. So this involves more than 1 qubits, and generally these are the kind of operators in which some qubits act as target qubits and some qubits act as control qubits. And only when the control qubits are essentially in a certain configuration that the operation is carried out in the uh, target qubit. So essentially it's like there are certain like hierarchy. So there are people whose permission you have to take to before you do a certain step. So if you have to like switch on uh, like you have to turn on a switch, so you have to ask somebody. So there are these hierarchies. So there are these control qubits which control whether an operation would be applied on a target qubit or not. So the simplest of the example is a C naught operator. So not operator, we know it flips from 0 to 1 or 1 to 0. So what C naught does is it adds an additional layer that only if the control qubit is in the state 1, that the not operator will be applied on the second qubit. Uh, I'll explain that in more detail. So this is how a C naught operator looks like. It's a 2-qubit operator, so that is why 4 by 4. So this is the basic structure of it. So let us say we are applying it on a state 0 0. So 0 0 is written in this way, 1 0 0 0. So as you see, the first qubit in this case is the control qubit, and the second qubit is in the state the target qubit. So since the first one is 0, the second one does not change. So it's 0 0. It remains 0 0. You can do the matrix multiplication as well, the same results. In the second case, the first one is the control qubit, it's still 0, so the second one doesn't flip. So it's again 0 1. In the third case, however, we have 1 0. So the first qubit is 1. So since the control qubit is 1, the not operation is now applied on the second qubit. So 1 0 becomes 1. So this turns C naught turns 1 0 to 1 1. And similarly for the last case, it turns 1 1 to 1 0. So I'll demonstrate the same thing in the Qiskit code. So this is the truth table. So 0 0 remains 0 0, 0 1 remains 0 1, 1 0 turns into 1 1, and 1 1 turns into 1 0. So in quantum like this Qiskit library, this is how we do it. So now we have a circuit in which there are 2 qubits and there are 2 classical registers. So quantum circuits 2 2. And we are adding a C naught gate from 0 to 1. So in this case, 0 is the control qubit and 1 is the target qubit. So as you can see, this dot represents that this not operation is being controlled by this 0th qubit. So then we add the measurement. So this block of code means the measurement of the 0th qubit is being stored in the 0th classical register, and the first qubit is stored in the first classical register. That you can also see in this case. So 0, it is stored in 0, and first it is stored in first. And then we display the circuit, and the rest of the course remains the same. So in this case, as you can see, the default value of the Q0 is 0. So the state initially is 0 0. So we expect the output to be 0 0. And again, we call the simulator, we do the whole thing, and we, as you can see, 0 0 100% of the time. So nothing changes. So now we do a little swap. So what we can do is we can take the control qubit and add a not operator on it, so that the control qubit is now in the 1 state. So what we expect is that this qubit will also be flipped now. So our state right now after the X operation is 1 0. So what we are expecting from this is a 1 1 state. So as we can see in this case, it's a 1 1 state 100% of the times. So this is how C naught basically works, and this is this is basically the multiple qubit operations. So now the towards the back end of my lecture, I just wanted to make tell you the difference between what a classical world and quantum world is, like based on this small talk, this small operations that I have showed you, to describe how quantum world and classical world are different. So the medium I'm choosing is a quantum toss. So what we can do is, so we know the basic how the basic like coin toss works. So it's either a heads or a tails. So you flip it, there is a 50% probability it will land on a head, a 50% probability it will land on a tail. So that the quantum analogous coin is this state. You see, this state, as I explained earlier, is a spinning coin. And once you catch it, there's a 50% probability it's either 0, 50% probability it's either 1. So this is exactly what it is. This is how exactly a coin behaves, right? So we can interpret 0 as heads and 1 as tails for even further simplifications. So this state can be created very easily by Hadamard gate. We have just seen the application. So what we are doing is we are creating this quantum coin toss. So toss, quantum circuit, one qubit, one classical register, adding a Hadamard gate and measuring. So what the result that we will be getting of 50% heads, 50% tails. So this is a very classical coin toss that we can simulate on a quantum computer. So as of now, there is no difference between the classical world and the quantum world. So this is like a normal coin toss. It's one of the two states. It will land 50% on the one state or the two state. To explain the difference, between a quantum world and a classical world, consider a coin, but which is being tossed twice, not simultaneously, one after the another. So let us say you had a coin, you flip it. You either gets a heads or a tails. Then you flip it again. The final state is again either heads or a tails. It doesn't matter what you got in the middle of it, right? So just to reiterate again, you have a coin, you flip it, you get a heads or a tails. You don't care. The point is the final state. You flip it again, you get either heads or a tails. I hope this is clear to everybody because this is the major difference point that we will come to. So let us try to simulate this exact same thing in our quantum circuit. So just to be clear, we have established that Hadamard gate creates a quantum toss. It creates a state which is 50% heads, 50% tails. So what we are doing first, we have a one qubit, one classical register circuit. We add the Hadamard gate, and we do a measurement. Then this barrier function it's a visual aid. It separates the two parts of the function. So the first toss, this is the first toss and the first measurement. So what we are doing is we had a zero qubit, we are turning into in superposition, and then we are looking at it. Either we got a heads or a tails. And then we are doing the second toss, the second application of the second Hadamard gate. And then we are seeing, okay, either we got a heads or a tails. The result that we are getting is surprisingly 50%, 50%. So 50% heads, 50% tails. This is exactly what we should be getting in a classical world. But the difference is that we cheated slightly in between. We did something known as measurement in between. So let's redraw this circuit, but remove the measurement that we had in between. So what we are doing right now is we had a qubit, we had a classical register. We added a Hadamard gate, that's one toss. Now we are not looking at this what the result that we are getting. We are just adding another Hadamard gate, we are tossing it again, and we are just looking at the final result. We are not looking at the intermediate result. So difference between classical and quantum, this will be the point. So in classical, we flip the coin lands on something, we don't look at it. We just pick it up, flip it again, either heads or tails. In quantum, we have a qubit, we add the Hadamard gate, either heads or tails. We don't look at it. Again, add a Hadamard gate, either heads or a tails, classically. So what happens is that we again do the measurement, and the result that we are getting is 100% of the times we are landing at heads. So we started at zero, we did two tosses, one after the another, and with 100% certainty, we are again landing at zero. This is not what we expected. This is not what we would get in a classical world. So to reiterate what this is classically. So let us say you had a coin, you started with heads, you flip it twice 1,000 times, and all the 1,000 times you got heads again. Impossible, right? So what exactly is happening in quantum world? So this is where I'll try to bring a little bit of physics to explain where this weirdness, where this quantum superpositions and these quantum operators comes into play. So what happens is that in classical world, see, measurements don't play that big a role because you have flipped a coin, you know it's going to land on a heads or a tails. There is no mystery there. It's going to fall on the ground. It's going to be either one of the two states. You can pick it up and spin it again. The difference is in quantum mechanics, the particles can stay in these intermediate spinning states forever. There are principles, so most famously Heisenberg uncertainty principle, that allow these particles to have indefinite momentum and position. So they might be just roaming around. They can be spinning around forever at a place. So that is why measurements play such a big role. So that is where the big difference between quantum and classical results actually is. So with this, our quantum coin it will keep spinning. It will keep spinning. So until unless we look at it, we don't know what it is. So that is where the second application of Hadamard gate technically brings it down to its same state that it was. So I'll show how how it works mathematically. So let us say there was some measurement in between. So what happens was, you starting with the first toss with on the zeroth state, you were getting a superposition between 0 and 1. You were doing a measurement. So once you have done the measurement, you will get either a 0 or a 1. And then you apply Hadamard gate on either of the two, you're again getting a superposition. Then you will again get either a 0 or a 1. However, if there was no measurement, now what happens is, if there was no measurement, you had a superposition state, right? Then you apply the Hadamard gate on this superposition state. So H2 on 0 will give you 1 by root 2 0 plus 1 by root 2 1, and H2 on 1 will give you 1 by root 2 0 minus 1 by root 2 1. So this 1 state cancels out. So essentially what you are left with is a 0. So, and even more, if you, the matrix, I think, operation we have talked about a lot. So what happens is that if you don't measure in between, what you're doing is you are like applying H twice. So that's the H square operation. And mathematically what it does is, H square is essentially equal to identity 1. So if you don't do a measurement in between, so you are essentially doing nothing to the state H square. So this is the property which is known as unitary. So this is where unitary matrices and reversibilities come into play. So this is the mathematical structure of quantum mechanics. So if you apply this, if you apply a unitary matrix twice, it's essentially going to give you an identity. So that is why measurements, that is why interactions, that is why these little things that probably in a classical world we don't pay so much attention to, they have so much importance in this class in quantum worlds. So this was just an attempt to show you the difference between quantum and classical worlds. And so the thing is, I do have quantum entanglement as well prepared, but it's much more mathematically complex. And I think even for a sitting of 30-35 minutes to go through this much already drains somebody. So I'm not going to go through quantum entanglement codes and everything. So I'm just going to tell what quantum entanglement is, and then that is where I finish off. So what so famously Einstein called it spooky action at a distance, if somebody has followed Einstein's career. So technically speaking, a quantum entanglement is a phenomena when quantum states, essentially they are not independent. The measurement on one somehow affects the other. So there is a certain correlation between them. So let us say again, I am sticking to the coin example. So let us say you had 2 coins this time. So one in one hand, one in the other hand, you flip both of them. So the possibilities that you have is either you get heads, you get tails, heads, you get heads, tails, or you get tails, tails. But what happened? But you see, like the whole point of it is, it doesn't matter what I get in one of the coins. The results of the second coin are independent. So first could be heads, the second could still be heads or tails. Similarly for vice versa. But what if we can do? What if we can produce a state in which if one of the coins is head, the second one has to be heads, and if one of them is tails, the other one has to be tails. So the measurements are not independent anymore. So this phenomena is known as quantum entanglement. There is way much more into it. That is why I'm not going into it. There is a lot of mathematics involved as well. So yeah, I did had the mathematics and all that stuff, but again I think it's way much more to cover. Quantum computation is such a dense and difficult topic. It's very hard to condense everything in 30-35 minutes, but I hope it's you get something out of it. I think that's the point of it, because it's very difficult to again learn everything in a span of 30 minutes. So with that I will end it. So these were the final quantum entanglement slides. So yeah, so this is it. The final note: there are many applications of quantum computation: finance, machine learning, optimization, scientific problems, quantum internet security, cryptography, all this stuff. I am particularly working in scientific computational problems, where my field of study would be applications of variational quantum algorithms in quantum chemistry. But the scope is infinite. So I hope you get something out of it, and you try to get into it. There is so many applications of quantum computation right now. Every day some breakthrough is coming up, and it's really fascinating. And I hope you enjoy this journey if you choose to. The last thing where you can find me: So these are my socials. So in case you want to interact with me, or there is some collaborative work that you want to get in touch with, there is some doubt that you have, maybe I, these are the places that you can find me. And that's pretty much it. Just last references, these are the books that I follow, these three books that I really encourage everybody to go through. Qiskit textbook, it has all the codes that you will need to understand at least the basic circuits. The new Qiskit textbook is also there. It's a beta version, doesn't work that well, but again, and I added an image, so I had to credit that as well. With that, thank you very much. Again, thank you Python Airline for providing me with this opportunity. It was a lot of fun, and I hope I was able to at least convey some of the things that I wanted to convey. Thank you.
Well, thanks you, Harshdeep. So that was, like, was this science or magic? It's hard to tell from where I am. So everyone, if you feel like maybe asking questions, we have the chat, or even better, the Q&A tool. If you want to direct a few questions, I certainly hope you do. If you don't, I have plenty anyway. Ah, that's okay. No, we have a shy attendance tonight. Okay, no questions. Okay, well, I do.
Yeah, go ahead.
Okay, so when you execute the simulation, you talk about the backend. That makes me think you're talking to some kind of other services, other machines. So, which would that be? Or, in my confusion is, okay, I have a computer here. I have it improved over the years. It used to be a massive thing, and I still have a few
Mhm.
of those. And now they are small laptops, but I still understand more or less how they work. And I can probably build a calculator from scratch, with just wires and orange, or a lemon to produce electricity, and build a calculator out of that. Probably with NAND gates, I could achieve that. Now, I'm not saying I want to build a quantum computer at home, but is there such a thing as a quantum computer? I mean, do they exist, or is that just a, a way of the mind? I'm
No,
that far
there.
away from what it is.
So small scale quantum computers do exist. So we do have quantum computers. So they have to be in a very specialized environment. So most of them are like so they are like superconductors, and they require a lot of moving parts. So they are like the supercomputers that we have. They're very specialized. The number of qubits is quite low. So the IBM's, I think the ones that is publicly available has around 50 qubits, and a fully quantum computer would require upwards of like 1,000 qubits. So we are far, but we are making tremendous strides towards it. So actual quantum computers do exist, but yeah, so they are not that much publicly available. They are the publicly available that they are around 50 qubit. So you can go to IBM quantum experience, and you can actually submit your circuits to an actual quantum computer. The quantum computer that they have, I think in their headquarters somewhere, I forgot the place. So it will get queued in the line, it will be executed in an actual quantum computer, and you will get the results back. So that provision is there. Quantum computers are actually there. They are not fully functional yet. That's the problem. So there is a very small scope right now of what we can do with these small scale quantum computers, but there are. So these things are coming up, and hopefully in a few years times we might be seeing some fully functional, fully operational quantum computers.
Okay, so you say nowadays they have a few qubits,
Yeah.
in the future, or to get something useful out of them, we will need a few thousand of them. So I have probably have completely missed the point, because in my world I consume bits by billions, by by
So
millions, to
see,
say the least.
yeah,
And even in my brain, if I were to make, as if I teach to uh, the new generation how to make an addition in binary standards, so even though I will consume a few dozens of them, So what kind of algorithm are available, or if something silly like, okay, sort a list, or is there such thing, or all those concepts are completely outlandish in that world, like a list
No,
of qubits? Would there be such a thing, or is that too far away an abstraction?
no, it's not that far away, because the problem is that the thing is, you said you need billions of bits for everything to work, right? The thing about qubits is that the linear combinations are possible. So even if you have two qubits, you can create infinite number of states with those two qubits only, because you can add them up with different parameters. So like these alphas and betas, these are real numbers, right? So even if you have two qubits or a single qubit, you can create like infinite number of states between them. And so that is why these only 1,000 qubits would give you a very fully functional computers. And so the algorithms that you're talking about, so the search algorithms are actually fully functional. So the Grovers and these Shor search algorithms. So these algorithms, we don't have the qubits yet, that many that we require, but we have the algorithms ready. So we have the variational quantum algorithms actually ready. So these things in theory are ready, and in practice as well, they are being applied right now. So so if you have seen that, I'm not sure if you will be aware of that. So the Google's Sycamore, I think that was their quantum computing program. So the task was, you had a quantum circuit, you had to sample it 1 million times. All right. So they did it. The point was to do it in a quantum circuit which had around, let's say, 50, 100 qubits, and your fastest supercomputer. The fastest supercomputer, in theory, would take to solve this problem, to sample all this problem, 10,000 years. The quantum circuit did it in 200 seconds. So it's not abstraction anymore. It's just a matter of time before it becomes, because these are like ultra cold, you have to keep them at 4 degrees Celsius. So it's very hard to like be like freely available to public, to have a quantum laptop. I guess that's that's a very far away idea, but quantum computers are being made, and I think that's something which we can see like and one other thing was that as you might have noticed, so somebody also pointed that in the chat as well. So the performance is increasing exponentially. That is true, because so the number of states that you get with each qubit is 2 raised to power n. So if you have a single qubit, there are two states that you have, two. If you have two qubits, then there's four. It increases exponentially with each qubit. So let us say right now you had 50 qubits, it's 2 raised to power 50. The next time it's 2 raised to power 51. So even if you have 1,000 qubits, then you have 2 raised to power 1,000 states to work with. That's a hell lot, considering a single qubit can be able to map infinite points on a block sphere or things like that. So yeah, I get the like curiosity point of it, but yeah, this is pretty much the reality, and pretty much the reality that we will see in a few years.
Scary. Okay, so yes, yeah, obviously you answered Vadim's question. Okay, so what with all our secrets and our encryption stuff when this is available? So the first one to get will share with the world, or will get, a rush to steal the machine. And I hope you mentioned 4 degrees Kelvin, because you're talking to Python Island, and 4 degrees Celsius is not uncommon here.
But like there is much more to just the temperature, right? But yeah, there's much more to it, in the sense maintenance becomes very difficult, because there is like, so a single qubit is that you in I think the most commonly used quantum qubits are made from like transmons or these trapped atoms. So you have to keep them, you have to place them in lasers. So there are a lot of like moving components. So so yeah, it's a logistic issue. So I don't know when the publicly available quantum computers might come, but public fully functional would come soon, because a lot of like right now, though, a lot of banks and also have started all these JP Morgans, these banks have also started investing in that. China recently, I think a few days ago, just announced that they had a major breakthrough in encryption and everything. So yeah, so everybody is aware of the fact that if a fully functional quantum computer came to existence, the first thing is anybody gonna do is completely like do the classical encryption, get away with it, and yeah, become uber rich. So that is why everybody is bracing for this. Everybody is getting into quantum cryptography and encryption and quantum key distribution. These things are picking up so much fire because people are aware of the dangers as well.